네, 안 돼. 이거 어떻게? 네? 녹화용이에요. So today I'm going to give a talk about Lindelof hypothesis on average for triple product L functions, and I'm going to also give some applications of it. So to begin with, I would like to first describe the motivating conjecture for why we have to care about the triple product L function. As in, first, there's a theorem by Zeldich, which is called quantum ergodicity. And his theorem states that if Mg is a pair which is a compact Riemannian manifold, and if you're given a orthonormal basis of Laplacian eigenfunction, then one can find a density 1 subsequence of it, so that the volume measure weighted by this eigenfunction converges weakly to the volume form, as in when I runs through the indices contained in A. So this is the theorem, quantum ergodicity theorem, and quantum unique ergodicity conjecture, which I'll call QUE conjecture, states that if M is negatively curved, as in if sectional curvature is bounded away from 0 by some negative constant, then this is true for whole sequence, as in there's no exceptional eigenfunctions which will contribute like density 0 subset. So the reason why we have to assume that M is negatively curved is because if we think about spherical harmonics on the sphere, then one can actually find a subsequence of eigenfunctions which does not converge to the volume measure. So for example, if you think about the Gaussian beams, which is concentrated basically on the equator, then the limiting measure will be supported on the equator. So QE conjecture is only for M being negatively curved. Yep. Mm-hmm.
On the left side.
Left side is dVg weighted by this eigenfunction at each point. So because this is number theory seminar, I have to give connection to why this matters for the person who studies number theory. So the connection comes when we assume that M is our favorite hyperbolic surface, which is H mod SL to Z. So it'll look like this. Then it is well known that mass forms if you consider mass form on this surface, then they are automatically Laplacian eigenfunctions. And we usually assume that they are all joint eigenfunction for Hecke operators. So say Vj is mass Hecke cost forms. Oh, before that, I have to mention that this statement here in this context is equivalent to saying limit of j So say you are given a sequence on any orthonormal basis of L2 of m, then if for each fixed n, if you compute this, and if you let j goes to infinity, and if this is equals to 0 for each fixed n, then that is the same as QE conjecture, provided that fn f the first eigenfunction is 1, so that everything else integrates to 0. So to be precise, this means that so QE conjecture is basically equivalent to this statement down here, and if we assume that Vj's are mass Hecke cost forms, then this is in fact a theorem by Lindelof and Sunderland. So I still haven't got into any L function business yet, but before that I would like to state another conjecture, which is quantitative QE conjecture. So QE conjecture tells you that the limiting measure given but weighted by Vj is the volume measure itself. And quantitative version of this will be about the rate of convergence to 0. So QQE conjecture is Vj there exists some positive constant nu such that this holds, where Tj is the eigenparameter for the Vj, as in Laplacian eigenvalue of Vj, C, is given by 1/4 plus Tj squared times Vj, C. So this is the quantitative QE conjecture, which is the quantitative version of this QE theorem. And although they could prove that the limit, the weak limit itself has to be the surface measure, but they didn't prove the rate of convergence. And in many applications, you actually need this rate, this small number, no matter how small this is. Having this number in your hand or not makes a lot of difference. Now I can state some number theoretic formula, which is, so say, because you can take any kind of orthonormal basis. Say you're given, you take Fn to be the mass Hecke cost forms, as in say you consider this integration, and see if this converges to 0. But then by Rankine triple product formula, which was originally developed for the application to gross product conjecture, for example, we can use that formula here. As in, if you square this out and divide this by the L2 norms of these three functions, then this is in fact equal to some constant times the central value of the L function given by the triple product, Rankine triple product between among these three functions. And you have to divide this by the adjoint representation associated to each mass form. So this normalization basically amounts to this normalization on the left-hand side. And for these, you actually know the very sharp bound for these. So basically you don't need to care about this. But then the thing matters is up here. And in fact, the quantitative QUE conjecture, the statement of having rate here is equivalent to subconvexity estimate for this triple product L function. As you can see from this equation, if this thing converges to 0 with some rate, then that will give you a bound for the L function in terms of the eigenparameter or in terms of the conductor of this orthomorphic representation. So from this equation, we see that this QE conjecture, which originally has nothing to do with number theory, has some connection to the study of orthomorphic L functions. And then because quantitative QED conjecture doesn't depend on the choice of f and z, so I'm going to choose f and z such that we can explicitly compute this integration. So let's take fz to be the Poincare series given by this test function h, which is by definition for gamma inside, let's call SL2Z gamma, and let's call this parabolic subgroup gamma infinity. Then Poincare series given by with the parameter m and h is given by h, y, gamma z, and e, m, x, gamma z. And here I'm using the notation that e of something is exponential to the 2 pi I x. And then if you plug in this Poincare series in place of f and z, then what you will be getting is by unfolding using the periodicity of phi j with respect to gamma, and because PMHG is invariant under action by this, actually it is periodic with respect to gamma as well. But then I'm going to unfold this integration so that this is equal to gamma infinity with h 3j x plus 3jz squared times So because I have amounted every gamma action in this coset by unfolding H mode gamma to H mode gamma infinity, I can actually have this simple expression. And then denoting by lambda phi n the nth Hecke eigenvalue for phi for this mass form, you can actually write this down as a sum of shifted products between Hecke eigenvalues times 0 to infinity. So you can actually get this by using the free expansion for phi j, and then if you plug in, then the term with exactly m difference will survive, and everything else will go to 0. If you do x integration first, then you'll be getting this. And some function n not equals to 0, and n has to be not equal to minus n. So from this, if you look closely what this function is, what you can actually prove is that quantitative quantum unique ergodicity is true if for any fixed test function h, one over t phi lambda phi n plus m times h n over t phi converges to 0 with some rate for some positive constant nu. So so I have to say that m is also fixed. In fact, this is stronger statement than having rate for this convergence of the measure, as in this function here, which I can approximate by compactly supported functions, doesn't actually cover every function. So that integral transformation has some subspace of functions which that cannot approximate. As in, so this is stronger statement, although it looks simpler than the original statement. And in fact, quantum unique ergodicity without quantitative rate is equivalent to having this n.
Right side doesn't depend on n. Right side doesn't depend on n.
The right side here? No, it doesn't depend on n because I'm summing over the Hecke eigenvalues, and that is intrinsic to the mass form. So this there's not.
There is a Ramanujan bound, isn't it?
Ramanujan bound is not sufficient. Ramanujan bound tells you that this is just bounded by some constant, and you can actually prove this quantity being bounded by some constant without using Ramanujan. So this rate actually tells you that there has to be some cancellation within n, the sum with respect to n here, and the optimal. I have to mention that the optimal rate of the cancellation we expect is the square root cancellation, as in this is basically the sum over t phi terms And if you have square root cancellation, then you'll be getting Tc to the negative 1/2. And then it is interesting that this square root cancellation is equivalent to the Lindelof hypothesis for the triple product L function. Having just any rate gives you a subconvexity bound, and having the optimal rate for the cancellation gives you the Lindelof hypothesis for the triple product L function. So so this also tells you that if this thing is true for any of these statements is true for almost all phi, then you recover quantum ergodicity theorem or quantitative quantum ergodicity theorem, quantitative quantum ergodicity conjecture. So quantitative version for quantum ergodicity was also not known by this point. And
It's like the working on banking, just electrical. You just get two. It's like the banking product, not the triple.
yes, because in this case, I have chosen the test function, which is equal to phi n. So that's why I'm getting extra phi n. And then because quantitative QE conjecture doesn't care about the test functions, I can take whatever function, and by taking it as a Poincare series, you actually get simpler statement. And that's the point of choosing this test function here, in order to make the computation untenable and make some theorems. Oh, I have to also mention that if you take that phi n to be the Eisenstein series corresponding to SL2C, then you'll be getting, you actually get the symmetric square times some Riemann zeta function for that triple product part. So QQE conjecture also implies the subconvexity estimate for the symmetric square L functions, which has not been known yet. So what I'm going to do, because having proving this, the rate version is quite hard. I'm going to study the average statement for this, and I'm going to have this rate for almost all phi. So what I'm going to study is T phi minus I'm going to look at this average of this quantity here, the average over phi. So I'm summing over every phi which has the eigenparameter close to t in terms of some extra parameter g here. So the optimal rate will be, if you have square root cancellation for every term, then this will be of size square root x, and square root x times 1 over x is 1 over square root x, and if you square that out, then the whole term will be 1 over x. And because there are t times g terms you're in this summation, the optimal bound will be t to the 1 plus epsilon times g over x. And then, so this is equivalent to Lindelof hypothesis on average for the triple product tail function. Surprisingly, if you can take arbitrary small g in this equation, then that is proving if you can prove this using trace formula with arbitrary small g, as in g equals to 1, then that implies t to the 1/8. So this is also connected to taking the Lindelof hypothesis for the Riemann zeta function, and all that, and this bound is better than any world record about this function itself. So it will give this method will give you some strong understanding on the growth of the Riemann zeta function on the critical line, and here's the theorem by myself. I could prove that this inequality when g is equal to t to the 1/3. And in this proof, I can actually recover the Weyl exponent t to the 1/6 plus epsilon, which is not the best exponent that is known right now, but then this technique here is interesting because it also gives you some nice bound about the Riemann zeta function on the critical line. It is something like 1/6 minus like 1 over 1,000 or something like that. So this is the best bound, whereas this is the classical Weyl bound. Weyl exponent. So I'm going to explain how one can actually compute this quickly. And in study of Mass-Hencke-Kost forms, there aren't many algebraic techniques that we can use, but then there are two advantages in having Mass-Hencke-Kost forms over just eigenfunction. So the first obvious thing will be, say you're given a free expansion. Then by assuming phi being Mass-Hencke-Kost form, you can actually relate this Fourier coefficient by the nth Hecke eigenvalue. So this is one nice thing. You can bring in the Hecke picture into the study of mass form in this expansion. And then the second thing, and also from this you have this Hecke relation. Ooh. And this is very critical input in study of mass forms. And the second input is if phi is L2 normalized. So this is the usual normalization of mass-Heike-Kost form in the context of spectral geometry or any analysis problem. Whereas the convenient normalization will be by taking the first Fourier coefficient equal to 1. So here's one nice thing about L2 normalized mass-Heike-Kost form, which is theorem by Hofstein and Lockhart, which tells you that lambda phi 1 is less than t phi to the epsilon and greater than t phi to the minus epsilon, which tells you that two different normalization of having L2 norm equals to 1 and having first Fourier coefficient equals to 1 is actually almost the same. So you don't really have to care about the choice of normalization. So these are two main ingredients in studying mass-Heike-Kost forms, and every other techniques can be derived from these two. So these two really are the central techniques. And so how I am going to apply these two techniques to here is that when you want to use Kuznetsov trace formula, then you have to have L2 normalized Fourier coefficient, not the one being normalized by the first Fourier coefficient equals to 1. So you cannot apply Kuznetsov trace formula directly to this expression. So in fact, you have to have rho phi n plus n and rho phi n. But then the trouble about applying Kuznetsov trace formula here is that when you expand this, you have some multiples of four Fourier coefficients, and you have to bring it down to a product of two Fourier coefficients in order to apply the trace formula. So that's where I'm going to use this. So, and then, so basically I first have to apply the first observation, which is rho phi 1 times 1 squared times lambda phi n plus m times lambda phi n. And then I apply the Hecke relation, which will give me times d dividing m lambda phi n plus m times n over d squared. And then this will give me rho phi 1 times sum over d dividing m times rho phi n plus m and d squared. And then I'm going to ignore this unwanted contribution using this estimate, and then resulting expression will be products of any two of these, in which you can apply Kuznetsov trace formula. So So the Kuznetsov trace formula looks like if you sum over product between two L2 normalized Fourier coefficient of mass forms, then if you put some contribution coming from Eisenstein series, then you get delta of n times some constant depending on h plus sum over Clusterman sum. Did I use G somewhere? And this function G is also given in terms of integral transformation of H. So you can apply this to this sum here after transforming that sum into this form with neglecting this contribution here. That's why that's one obvious place where one can see that one needs to put t to the 1 plus epsilon rather than just t here. I'm already ignoring some t phi to the epsilon contribution, so one has to amount to that contribution by putting epsilon here. And because epsilon can be arbitrarily small, it doesn't cause that much trouble. So if I apply Kuznetsov trace formula to this after transforming like that, then I'll be getting sum over this sum being less than some main contribution plus some off-diagonal contribution. And the off-diagonal contribution will contain a lot of sums over Clusterman sums, sums of Clusterman sums. Therefore, in the end, the typical shape of the Clusterman sum that I'll be getting after doing computation here is, before that I have to give you the definition for a Clusterman sum. So the Clusterman sum is sums over exponential. So it is one of the very central exponential sum in the study of mass forms. So C over nx plus nx bar. This is sum over x modulo c, where x and c are coprime. And this x bar means multiplicative inverse of x mod c. So this is the Clusterman sum, and if you apply this formula to that shifted convolution sum, then you'll be getting a bunch of Clusterman sums. And then one typical sum that you'll be seeing is this is precisely when m equals to 0. When m equals to 0, then you get this sum by computing these, and you have to estimate this. And when m is not 0, then you have some extra terms inside this expression. But morally, the idea is the same, to control this sum here. But then x bar is the multiplicative inverse of x modulo c. Yeah. But then, if you just apply value bound for the Clusterman sum, which is S n c is less than or equal to n c, then the bound for that sum you'll be getting is far worse than the bound that we are aiming for. So value bound is not enough to apply in this context. So we have to do something better than value bound. Value bound is sharp. One can actually find a lot of Clusterman sums which actually achieves this equality here. But then because we are summing over this number of divisors sub C. Maybe I should D0. C looks better. And then one observation about this sum here is that if you don't care about C and if you just consider the sum over A, then that is actually a Gauss sum, which one can evaluate explicitly. And then you can take sum over B, which is again a Gauss sum. So if you if you evaluate Gauss sum twice, then you actually get, if I call this SC, you actually get SC is essentially less than C to D 3 over 2. So, which is far better than applying value bound into this sum, which will give you C to D 5 over 2. So if you don't consider the cancellation coming from sum over A and B, then you'll be getting C to D 5 over 2. But then if you just evaluate the Gauss sums, then you'll be getting C to D 3 over 2. So you have extra one C saving in C. And this actually, in fact, if you play this with some special C's, for example, if you consider C being a prime, then this bound is sharp. One can actually find SC almost equal to C to D 3 over 2. So after applying this into the sum, then I get the right bound for the average of the shifted convolution sum, and therefore that implies the Lindelof hypothesis on average for the Rankine triple product L functions. So original motivation for doing this is to find do some LP restriction of mass Hecke-Cos form on the surface. So LP restriction estimate of phi means that take gamma curve, for example, on the modular surface, and LP restriction estimate is estimating the LP norm of phi on gamma. And if one uses only analysis technique, the ones we are getting for this LP estimate are really bad. So for example, if you consider L infinity norm on the whole surface, then by using analysis technique, one gets 1 over 2 plus epsilon. But then if you use some extra information coming from assuming phi being mass Hecke-Cos form, one can actually prove 5 over 12 plus epsilon. But then this bound here in general is sharp. But because we are assuming mass Hecke-Cos form, we are getting some better exponent here.
So what's the expectation?
L infinity conjecture by Sarnak and Iwanich is T phi to D epsilon. If one take C being some compact subset of the surface. So this exponent is due to Iwanich and Sarnak in 1995. And there has been no improvement on this exponent for even single Maseke-Cusp form. And then as an application for my theorem, I could actually prove that this is less than T phi to D 3/8 plus epsilon for almost all phi. So this is in fact the very first example for finding Maseke-Cusp form having better L infinity bound. And using this, I could also prove that VIY, the L2 restriction to if one considers the L2 restriction to this short segment along the imaginary axis, then it is not necessarily true that this has to be converging to some constant. But then I can prove that this stays away from 0 for almost all phi. And then in the end, if you combine this information with this, and because we know that the Lindelof hypothesis on average for this L function, which is attached to a mass form. What I can prove is for almost all phi has at least T phi to the 1/8 minus epsilon nodal domains. So the bound that Ghosh and Reznikov and Sarnak achieved using Lindelof hypothesis was T phi to the 1/4 minus epsilon nodal domains. And then this tells you that without assuming anything, you can actually do better for almost all of them. But there might be some exceptional thing which has smaller nodal domains, but I couldn't exclude that yet. So this is end of my talk.